Hello, everyone. Before I get started, I want to thank you all for coming today. And I would also like to thank CaseBlink for sponsoring this Tech Talk. So today I want to talk about sockets. But before we jump into the talk, I kind of want to go over sort of an overview of how I approach this talk. So first, I want to start with a brief history of Internet protocols. Next, I want to identify the main problem that sockets address. And then I want to talk about the difference between TCP/IP and UDP/IP, which are two really common internet protocols that we see today that implement sockets. And then finally, I want to wrap things up with some tools that are available today for JavaScript developers and show just how easy it can be to set one of these things up. So you've probably seen these four letters before, HTTP. It stands for Hypertext Transfer Protocol, but what does that actually mean? Well, a protocol is a series of regulations that dictate how an operation is done, and this is no different. So when you put HTTP on a URL, you're defining a set of rules that the network request will abide by. And while it's pretty assumed what sort of protocols you'll use now, this was not always the case. Let's go back to the early 1980s, before the internet was even publicly available. Up to this point, companies had built their own proprietary protocols for internal use and were starting to run into some trouble because of it. Companies like IBM were struggling to work with vendors like Cisco because data transfers were complicated and unwieldy. It got to the point where national governments were getting involved by funding standardized protocols. These efforts led to the OSI, or Open Systems Interconnection Model, which is a close relative to TCP/IP, or Transmission Control Protocol. This acronym might seem unfamiliar to you, but you've actually already been using it all the time. See, much of the heavy lifting today has been abstracted away from developers because of the standardization of this protocol. So what you really need to know is that the TCP is conceptualized in terms of layers. And at the so-called application layer, that's where developers interface the most, and we use the protocol HTTP. So when you make a fetch request or you visit a website, the request that you make to the server has to abide by a set of rules and regulations. These requirements might look different depending on the protocol, but in the case of HTTP, some example rules are that certain headers must be sent with each request. It might follow a specific process, such as a request being made, and then a response coming back from the server with a status code or other data. One hallmark trait of the HTTP is that it is fully terminated upon completion, meaning that an entirely new request will have to be made to reestablish connection to the server. And that detail is rather important for applications that require low latent real-time rendering. It presents a real problem for developers that want to develop live interaction applications like chat rooms or online multiplayer games. So what are some of the ways that developers have solved this problem and achieved real-time user interaction? First, I present the "Are we there yet?" model. With this strategy, you fully embrace the existing architecture of HTTP and use a sort of polling technique, which involves endlessly pinging the server at a fixed interval. This sort of process introduces a lot of unnecessary overhead, but it actually could have some use cases if an application was willing to stomach the network stress in order to get millisecond specific data response. That said, these use cases are far and few in between, so let's keep looking. Next up is a close relative to the "Are we there yet?" solution, but it's a little bit more mature. Formally, it's known as long polling, but I like to call it the desperate lover strategy. Essentially, it operates like polling, but the polling doesn't respond unless it has data. So it spends a large amount of time potentially waiting just to receive a small amount of data. And if too much time elapses or it receives data, then it will reopen another request immediately. So this strategy is slightly more efficient in that data transfer is guaranteed with every request, aside from a request timing out. That said, you can still run into the same issue of network overloads if you receive a ton of requests at once. And that brings us to the namesake of this tech talk, which is sockets. Sockets, and particularly WebSockets in our case, look at the previous two solutions and just asks, why not just maintain the connection? It introduces a useful strategy, which is just don't break the connection after the request is made. Its strategy is to open a bidirectional, fully duplex relationship between the client and the server. At a high level, that's the main fundamental difference that gives sockets a huge advantage over polling and long polling asynchronous techniques. So, how does it actually do this? Well, establishing a WebSocket connection begins actually by just making a normal HTTP request. However, when that request reaches the server, a request is made to level up the connection. The server gracefully responds to this, and with that, the famous handshake is complete. The connection upgrades such that either party, front or back end, can send data and receive data in real time. So there are several different types of sockets that are commonly referred to, but I want to focus on two that are really prominent today. At a high level going forward, you should associate sockets with bidirectional flow of data, meaning that instead of one actor, such as the browser, serving as the primary sender and the other acting as the receiver, either the server or the client can send information. At a technical level, you should know that a socket usually offers some sort of advantage that defines why people use it, such as having its connection persist, where other connections might be terminated after receipt of data. And at a basic level, you should know that a socket is just an endpoint that's capable of doing cooler than usual stuff. So with that, let's chat about two prominent socket types. They are the most common to see implemented, and they differ based on their protocol or rules that they follow. So they are stream sockets and datagram sockets. Stream sockets are guaranteed delivery, and if an error occurs during transmission, the sender receives an error indicator. Sent data also maintains its order, meaning that if you send A, B, C, it will arrive in that order A, B, C. And for these reasons, it's considered sequenced and reliable. Now, datagram sockets, on the other hand, are not guaranteed delivery to their final destination. They also do not care about the ordering. So if you send A, B, C, the server would be just fine with receiving A, C, B. And for this reason, it's considered not sequenced and not reliable. And if you're anything like me, then you look at these two and you say, well, it sounds like stream sockets are the way to go. But like everything in software engineering, the tool you use should be predicated on the use case. And as it turns out, UDP, being somewhat of a troublemaker, actually has some benefits. So take, for example, online gaming. This is heavily reliant on datagram sockets and therefore UDP IP. If you experience lag in a game like Call of Duty or Halo, the game doesn't stop. You're allowed to still move around and often see the other players moving around as well, despite there being a connection issue. You might fire at someone and do no damage, and you might take damage despite no one shooting at you. This is because the protocol of datagram sockets allows for unsequenced data. So you're receiving data that someone has shot you, but you're unable to see them because that data hasn't arrived. This leads to a more pleasant user experience that, despite having network issues, helps keep the user more engaged. Imagine that every time you experienced a little bit of lag, a message came up freezing the game saying that the game had to synchronize because of a lost data packet. Who would play that? Conversely, let's take a look at stream sockets using TCP/IP. Let's say you want to download a file like a software installer, which is an executable file for your OS. You're going to need every single byte downloaded in order to use that file and to avoid some sort of corruption. Using stream sockets will give you better guarantees of correct file transfer because its protocol will ensure all packets of data arrive in the correct order and that there have been no errors. So in conclusion, they both have their use cases. Sometimes you need that extra flexibility, and sometimes you need a more exact approach. So when your interviewer asks in a TI what WebSocket implementation you'd prefer, you should probably start with something like, well, it depends, before explaining. Now, considering this is a talk for JavaScript developers, I want to pivot slightly and show off some language-specific tools that you can use today. We'll start with a brief overview and then dive into one specifically. So this WebSocket API has risen to the top of popularity because of it mainly its simplicity. It abstracts away a large amount of setup required in other socket libraries and is widely supported across many browsers. One of its downsides is that it has no built-in broadcast feature, meaning that it cannot send a message to multiple clients at once. Now, Socket.io, this API has become really popular lately because it introduces a few extra security features, like having a fallback feature to use long polling in the event of a connection error. So this API's strongest and greatest weakness is basically the same thing, that if you don't end up using those extra security features, you could have some unnecessary performance overhead. Next up is Net. And so Node offers both TCP and UDP socket APIs that are native to its runtime environment, which is great because that means that their functionality is not limited to web-based applications. That said, the application is dependent on a Node backend. So if you ever need to migrate frameworks, you may experience different functionality or behavior than expected. And then finally, WebRTC, which is a highly versatile framework that's configurable to UDP and TCP. So it offers the developers a lot of flexibility, but it comes with the setback that it's more complex to set up and could be more complex to manage compared to above solutions. So at this point, you're probably wondering, what does it actually take to set one of these up? So I figured it'd be a great time to show what the startup process might look like in a JavaScript application. And with that, I'll jump over to a really simple live chat application that I made in React. So you can see here my app.js, which is my front end file here. All you really have to do is import IO from socket.io client, and you can see that I'm using socket.io API here. And then you instantiate a socket, and you invoke IO and pass in your endpoint. Then all you have to do is basically give the socket some instructions. So use this on property to say, okay, listen for a chat message. And then when you receive that message, do stuff. And this is a function that I passed in here. So it will execute this when it receives this message. And likewise, down here, you can see a send message, where once the user fires this function, then the socket will emit a chat message out to anybody else who's connected to the socket. In the backend, it's just as easy. So we require in socket.io from socket.io, and then we attach it to our server instance by creating a variable here and then invoking socket.io and passing in our server. And then all we have to do is say on connection. So that means when a user connects to our endpoint, we'll have access to a socket object in the callback. And then we can give it whatever instructions we want, just like before. So when it receives a chat message, then we're going to have it emit that chat message out to anybody else who's connected. And the cool part about this is that we can see it right in front of us. So if user 1 sends a message, you can see that user 2, who's also connected through the WebSocket, receives that in real time. Likewise, if user 2 says hello back, user 1 receives this in real time. And it's really that easy. It's somewhere around 10 lines of code, and you've got a WebSocket set up. So with that, here are my works cited, and I would like to thank you all for coming today.